All right, our next topic under the area of solving systems of linear equations is we're going to start solving them algebraically. Okay, that's a little bit easier, I think, than solving them graphically, and you also are much more likely to get a precise final answer. So we're going to start solving them using substitution, using that method, and we'll start with an introduction and then do a couple examples in this video. All right, so a couple steps to follow. If you want to use the substitution method, you need to get a variable isolated for in one of the equations. It doesn't have to be x, doesn't have to be y, it could be either. It doesn't matter which equation it is, but you need a variable isolated for. And then you're going to substitute in for that variable in the other equation. Okay? So say you get y is equal to something, you're going to plug that something in for y in your other equation. You're going to solve for the remaining variable, which probably means solving for x if you substitute it in for y. And then you're going to plug that solution into either of your equations to solve for the final variable. And then, of course, check your work. Okay? That's a lot. It seems like it's a lot of steps to remember right now, but it should make a little bit more sense once we go through an example. So let's do that. We'll solve a system through substitution. All right, so here's, in our first example, we have a couple equations, and so presumably, again, these represent two separate lines that intersect somewhere, and we're looking for that point of intersection, which is the point that's common to both lines. So we're looking for sort of the one special point that happens to fall on both lines. So we have 5x plus 5y is 5, and we have y equals negative 5x minus 17. Okay, so here's what we have. We have y is equal to this stuff. So let's plug it in for that y right there in my first equation. So let's see what that turns into. So this is going to turn into 5x plus 5 times, now instead of y, we're going to put in the negative 5x minus 17. And that's still all equal to 5. So we just rewrote the first equation with, instead of y plugged into it, the negative 5x minus 17 plugged into it. Okay, so we substituted in for y. So we can go ahead and simplify some stuff now. We have 5x. We're going to distribute this 5. That's a negative 25x. That's 5 times negative 17 minus 85. And that is all equal to 5. Okay, so I am going to do a couple things at once here. I'm going to add 85 to both sides. And then I'm also going to combine some like terms on the left side to see what we get. So we have a negative 30x equals, once these 85s cancel, equals a 90. So I can tell we're going to get a nice clean answer. So that's handy. Let's divide both sides by negative 30. And we get an x is equal to negative 3. So that's good to know. X is negative 3. But we're not done. We need to figure out what y is as well. So we can take this x being negative 3 and we can plug it in anywhere we want. Anywhere we see an x. We can plug it in for that x right there, or we can plug it in for that x right there. In my mind, it looks like it's easier to plug it in to this second equation because that will give us y right away. We won't have to do any further algebra to solve for y. So let's do that. So we're going to turn this equation into y equals negative 5. And instead of x, we're going to plug in our negative 3 and then still minus 17. Y equals 15 minus 17, so y equals negative 2. So we've solved our system. I think it's best practice, though, to write your answer as an ordered pair. So negative 3 comma negative 2. So that's the actual point where those two lines would intersect on a graph. And then to do a check, I like to at least plug them into one of my equations to check. And if you really want to really make sure, you would plug them into both. But I'm going to do a check over here, and I'm going to plug that into my first equation. I'm pretty confident they work in my second equation because that's how I got my y value. But let's plug things into my first equation. 5 times x is negative 3 plus 5 times y is negative 2. And we're wondering, is that all equal to 5? So is 15 plus negative 10 equal to 5. It is, it checks out, so it looks like we did it correctly, so that would be our final answer. All right, let's do another example here with substitution. And this shows an example where we need to do that first step of actually isolating for a variable first. So we don't have x or y isolated for. I think it's really worth trying to be strategic and thinking about which variable would be easiest to isolate for. And I can see right away that if I add 2y to both sides, I'm going to get an x by itself, 2y plus 11. Okay, and then you have to keep track of which equations you've sort of manipulated and which equations are sort of your original equations. So if we tried to think of these two equations as our system of equations, we would get overlapping lines. Okay, we would get a dependent consistent system. Okay, so we don't want to use that equation anymore. We want to use these two equations now, okay, to do our substitution. So a lot of the challenge with substitution is with systems of equations is staying organized. So let's do our substitution right now, and we're going to turn that first equation into something a little bit different by plugging in what we know x to be now. And I hope you're seeing one of the goals here is to eliminate a variable. And so in this equation I just wrote out, there are no more x's. And so that's good news. We can solve for y. And first we'll distribute. And then I'm going to do those same couple steps. Let's add a 77 to both sides. And then let's also simplify the left-hand side. Negative 14y minus 2y is negative 16y equals a negative 13 plus 77 is 64. And we can go ahead and divide by our negative 16. And it looks like we're going to get y is equal to a negative 4. Nice. So we solve for y, so that's good news. We still need to solve for x. So we are free to plug this negative 4 in for a y value anywhere we see a y in any of our equations, as long as there's an x as well. So we wouldn't want to plug negative 4 back into that equation. That would just effectively be checking our work. There's no x to solve there. But we could plug negative 4 in for y in here, here, or here. Any of those guys would work. And I'm going to actually plug it into that highlighted one right there because it has an x isolated for it already. So we have x is equal to 2 times negative 4 plus 11. So x is negative 8 plus 11, which is negative 3. So we have our solution. We have our set of coordinates. X is negative 3 and y is negative 4. And that's where those two lines would intersect on a graph. All right, moving on to a couple special circumstances. I'm going to go a little bit quicker here just to keep our video a little bit shorter. But let's solve the following system of equations. So I think you can see that there are might be some curiosities going on here. This second equation I'm going to isolate for y by turning into y equals x plus 3. And then let's substitute it into my first equation. So I have a negative 3x plus 3 times x plus 3 equals 4. And simplifying, distributing, negative 3x plus 9 equals 4. It looks like a couple 3x's cancel, and we have a 9 is equal to 4. So what the heck's going on there? 9 is never equal to 4. So this means we have parallel lines, and what it really means is there are no solutions to the system of equations. So whenever we get an impossibility like that, 9 equals to 4, no, it's not, right? 9 is not equal to 4. That means we have no solutions. And then lastly here, let's go ahead and solve this one, another bit of a curiosity. I'm going to take my second equation, let's isolate for x by dividing everything through by 8. Okay, and what does that turn into? We have an x is equal to 4.5 plus y over 2. Okay. All right, so let's go ahead and substitute into my first equation. We're going to substitute that in 4 times what we now know is x equal to y over 2 minus 2y equals 18. Distributing, we get a 9 plus 2y. Wait, 4 times 4.5 is 18, my bad. Doing this right here. 4 times 4.5 is 18, plus 2y minus 2y equals 18. And maybe you can see what's about to go happen right here. Our 2y's are going to cancel, and we have an 18 is equal to 18. Well, of course, 18 of course is always equal to 18, no matter what y was, right? So this means that we have the same line, okay? It means we have an infinite number of solutions. Okay, so there are an infinite number of ordered pairs along those overlapping lines that would work. All right, that's a good place to stop right there.